Okay, so we are going to start the last section of the solutions unit with a special type of solutions, which are acids and bases. What we're going to do today is look at some of the theory behind acids and bases, and then the next few lessons will focus on a little bit of the quantitative side of it, and then next year in grade 12 we'll do much more detail. Okay, so and perhaps you have talked about acids and bases a little bit in grade 10. Okay, so I believe the yellow stuff you have to fill in. Some common acids, so citric acid, like in citrus fruit. So if you've ever, eaten an orange or something and you can, your sour taste buds are activated. Lactic acid is the acid produced by muscles that are metabolizing oxygen too quickly. So when people talk about feeling the burn, you're feeling the lactic acid produced by your muscle cells. And then acetic acid is the common scientific name for vinegar. Some common bases are sodium hydroxide. So in general, bases are thought to be a little bit safer because they don't cause corrosion as soon as they touch like skin tissue. So certain soaps have varying degrees or concentrations of sodium hydroxide. So something like Drano, which is actually a pretty powerful chemical, but you can buy it and have it in your home, is a solution of sodium hydroxide. And it will, like if you got Drano in your eye, for example, like you could lose your eye. Like it's not a very good, it's an intense chemical, but it's supposed to clean out drain pipes, right? So you can imagine the things you're kind of trying to digest that can be found in your sink. Whereas the solutions that we use in class are also sodium hydroxide, about 1 molar, and bases you can dissolve in water. So you can do, we have solid sodium hydroxide and we dissolve it in water to make a solution. Sodium bicarbonate is baking soda, the scientific common name for baking soda. And ammonia is also a cleaner. Now, pure ammonia, again, would be way too strong. In fact, when I was in high school, we did a lab with ammonia, which we don't do anymore. And my friend said that it smells like running your face across the driveway, which is ridiculous. But she was just trying to describe how pungent the odor is, and it was like assaulted her nasal passage. Okay, so that was her. And we don't have ammonia anymore in school, pure ammonia. So there you go. There, that tells you how dangerous it is. But some people describe the smell of Windex as ammonia. Plenty of forms of Windex don't have ammonia in them anymore, but sort of that smell that is often attributed to Windex. If you have some kind of small pet that's like a rodent, so guinea pig, rabbit, something that has to live in a cage, if you don't change the shavings, then it starts to give off this smell, which is ammonia. So if you remember from grade 9, the nitrogen cycle, one of the waste products of living organisms is like urine would break down into ammonia. So that's the smell that you're smelling. So, it's not gross like decay, but it is definitely a pungent smell. Okay, so of course we are in the solutions unit. So acids and bases have characteristic properties when dissolved in water. And acids, in fact, we've talked about this before, are always aqueous. So they are very common aqueous solutions. Bases are actually less common. So even next year when we do more quantitative questions with acids and bases, most of the questions will be about acids because they are just more common. Okay, so the acids that you are able to taste, like vinegar, citric acid, definitely have a sour taste. They will conduct electricity because they dissolve in water to make aqueous solutions with ions, and they cause dyes to change colors. So one of the labs you might have done in grade 10 was testing different indicators to see the color change. They are said to have no characteristic feel. Now, if you call corrosion a feeling, I guess it could feel corrosive. And the first indicator they used was called litmus paper. It turns litmus paper red. And litmus paper was probably one of the indicators you used last year. Bases, they will produce gas. So one of the main differences in terms of reactivity between acids and bases is when you put an acid with a metal, then you see bubbles of gas, and that gas produced is hydrogen. And they will produce carbon dioxide when reacted with carbonates. So maybe one of the first chemical reactions you ever did was putting vinegar and baking soda together, and you saw bubbles of gas, and that gas happens to be carbon dioxide. And then once you put it with a base, then it is going to start to neutralize, which means it will lose its properties, except there are still ions to conduct electricity, that are able to conduct electricity. Bases have a bitter taste. So again, if you've ever gotten soap in your mouth, that sort of bitter taste. Another good example is if you've ever taken medicine like Tylenol, that has no candy coating on it, like it's just like that white chalky substance, and you put it in your mouth and you can't swallow, like you leave it in there too long, that weird bitter taste you get is because it's basic. They also conduct electricity and cause an indicator to change a different color. So then the indicator indicates, right, it's in the name, whether it's an acidic or basic solution. Bases feel soapy or slippery, and they will turn litmus paper blue. So again, there's no reaction with metals and no reaction with carbonates, so that's a good test for whether you are dealing with acidic or basic solution. And again, it loses all the above properties except that it still conducts electricity. Okay, so the theories about acids and bases can be broken down into Arrhenius, which is a person, and then Bronsted-Lowry. So there's Arrhenius, Svante Arrhenius. And he said that acids and bases follow a pattern of dissociation when they dissolve in water, which is useful in helping to describe how they behave chemically and how they conduct electricity. So he said that acids ionize to produce hydrogen ions in water. So hydrochloric acid dissociates into hydrogen ions and chloride ions. So that's hydrochloric acid, a common acid that we use in the lab. And since acids produce hydrogen ions in solution, they are considered a source of these ions. And that is why what we calculate or categorize acids with is the pH scale, the power of the hydrogen ions. So, and we talked about when we did naming of acids that all acids have a hydrogen atom in them, and then when they are dissolved in water, then they will produce hydrogen ions. He said that all bases dissociate to produce hydroxide ions in water. So this is good for strong bases like sodium hydroxide. Sodium and the hydroxide split apart into the positive and negative ion. And again, since bases produce hydroxide ions, they are considered to be a source of these ions and increase the concentration of these ions when they are in solution. So his theory was good. It explained the ions produced when an acid dissociates in water, but it didn't explain all of the bases. So it's good for strong bases only, and we'll talk more in the next lesson about what makes something strong versus weak. And so when you were in grade 10, your teacher probably talked about an acid and a base, which makes a neutral water solution with a salt, right? So the most common example they use is hydrochloric acid and sodium hydroxide. So you get HOH, which is water, and you get sodium chloride, which is the salt that's produced. But then they just discovered that that's only true that you get a perfectly neutral solution when you mix two acids and bases together if you have a strong acid and a strong base. So that's where he was limited. So what they saw was this, once they could do chemical analysis, they realized that there was an ion being produced in water and they called it hydronium, and it has the formula H3O plus. So it's a protonated form of water. For example, water's H2O, so now it has an extra hydrogen, H3O. So what was going on there? Arrhenius's theory could not explain that. Also, substances like ammonia and sodium bicarbonate, HCO3, have basic properties. They will react with acids. They produce gases when they react with acids, all that kind of stuff that is a characteristic of an acid-base reaction, but do not have hydroxide ions in their formula. So what's happening there? How are we getting the hydroxide ions to make them basic and raise the pH of a solution? So we needed to expand the theory. So along came Bronsted and Lowry, these two handsome gentlemen here, and they revolutionized it. And actually, moving forward, in fact, if you take chemistry into university as well, they will probably stop using the word neutralization, and we'll talk more about proton transfer. So describing an acid as a proton donor or a source of hydrogen, which is the same as Arrhenius, so that's fine. But then the bases as something, a solution or a substance that can accept a proton, which expands the definition to include all bases. And it also helps explain how water can change from H2O to H3O positive. Okay, so how does that come about? So this is such an important definition moving forward. So this is where, tonight when you go to sleep, say it over and over again. Acid is a proton donor, base is a proton acceptor, until your parents come and say, please stop talking and go to sleep. Okay, so why proton? So when you have a hydrogen atom, then if you remember from the Bohr-Rutherford diagram, it has 0 neutrons, 1 proton in the nucleus, and then 1 electron. Hydrogen, of course, is in the first column of the periodic table, so it loses that 1 electron, sorry. And all you're left with is the 1 proton. So this is actually, calling a hydrogen ion a proton is actually a very common thing in chemistry and also biology. So those of you that are in biology will talk about proton pumps and pumping protons across the membrane, cell membrane and things like that. What they're actually talking about is pumping hydrogen ions across the membrane. And like I said, pH means the power of the hydrogen ion. This is a very common ion out there. So using this description for an acid-base theory makes a lot of sense and can be applied to a lot of things. So like I said, moving forward, you might find that your professors do not use the word neutralization reaction. They'll talk about proton transfer. Okay, so in grade 11, what we're going to do is I'm going to give you an equation, if we were going to do, even if we were in class and we were going to do a real test, then I would give you the equation. Next year in grade 12, you're going to be able to build these equations on your own. So all we have to do is label what's the acid and what's the base. So yes, I know that HCl is a common acid that you may have memorized, but let's look at what happening and describe them as donors and acceptors. So in grade 10, your teacher might have said that a base has to have hydroxide ions, but you can see here we have something happening. This ammonia, NH3, is reacting with the HCl, but it doesn't have hydroxide in it, right? So sometimes this is called an Arrhenius base, something that has hydroxide in it. So yes, that's possible, but that's a very limited way of thinking about whether something can be acidic or basic, okay? So if you look at this reaction, now it's difficult to do on the computer, but this NH4 NH4. Its positive would probably be more like that. And that is the ammonium ion. You guys are used to that, right? You've seen that before. So if you have NH3, then logically something has happened to it and it's become NH4 plus. What has happened to it? It went from 3 hydrogens to 4 hydrogens. And it also gains this positive charge because you're gaining a proton, which is positive, right? So the charge itself can be tricky, but what you're looking at is what's happening to this substance. So NH3 had 3 protons or hydrogens, and now it has 4. You can also look at HCl. HCl had a hydrogen, and over here, now it doesn't. It gave it away. It donated it, right? So then we call ammonia the base because it went from 3 to 4. So it went from H3 to H4 on the other side of the equation. It gained or accepted a proton. And the HCl is the acid because it went from HCl to Cl minus. It gave one away. It donated. The weird thing is we're also going to go the other way. Okay, so now what's going to happen is you have to label all 4 substances. So now on the other side, you have to decide what's the acid and what's the base. Normally, it's a little bit easy because this chlorine ion here, this chloride ion, does not have an H to give away. So it has to be the proton acceptor. But this one, you can also look at what it becomes. So now we're going to go the other way as well. So the NH4, and really it doesn't even matter about the N, you're looking at the H, becomes H3 if you go backwards. So it's an acid. But then again, this Cl has no H to give away, so it has to be an acceptor. So it's the base. Okay, and we'll do more of those. So like an Arrhenius acid, a Bronsted-Lowry acid has to contain an H. Or hydrogen atom, it's going to be a donor of the H. So just like we saw with that Cl minus, if it doesn't have an H to give away, that automatically makes it a base. But a base now can be anything that is an anion or negative. So yes, it can be OH or anything negative. So now the definition of what's an acid and what's a base described by this theory is ubiquitous. You can describe any acid or any base. So again, proton transfer, that term is going to become important. A proton is going to be removed from the acid or donated by the base, which accepts it. Another thing you can label are what's called conjugate acid-base pairs. So you want to label molecules or ions that are related by the transfer of a proton. So this definition here is a little bit strange. This one's more important. They are related by the transfer of the proton. So NH3 became NH4. They are a conjugate acid-base pair. So you want to have a base and an acid in each pair, or an acid and a base. So back to this example, you have NH3, which is the base. It accepts a proton to become NH4. HCl is an acid. It donates its proton to become Cl minus. So Cl minus is the base because it has no proton to donate. And then NH4 is an acid. It goes from NH4 to NH3. Excuse me. So when we label conjugate pairs, you can use these like arrow kind of things. So NH3 is a base, which it accepts a proton to become NH4, the acid, so they are a conjugate pair, and HCl donates a proton to become Cl minus, its conjugate base. So NH3 and NH4 are a conjugate acid-base pair. HCl and Cl minus are a conjugate acid-base pair. So this is a base and its acid, an acid and its base. So you're not pairing up the acids or pairing up the bases, you're pairing up the substances that are related by proton transfer. So NH3 and NH4 almost look like the same thing. HCl and Cl minus almost look like the same thing. They're just different in terms of one hydrogen. And for now, even in grade 12, we're only going to transfer one hydrogen at a time. You don't have to worry about trying to do 2 or 3. Okay, so let's do one more example. So now you're looking, this HCN, what does it become? So you look at the products and what makes sense. Does it make sense that it became H3O? No, that doesn't make sense. Does it make sense that it became CN? Yes, they almost look the same. How are they different? The HCN has one more proton than the CN. So that means that this HCN is the acid. To this conjugate base, and they are related by proton transfer. H2O becomes H3O. So this one now went from 2 to 3, so it gained a proton. And then the H3O is able to give one away, so it's the acid or the donor. This is not easy, okay? And so I just recommend you try as many as you can. Like I said, in grade 11, you don't have to write your own reactions. You just have to be able to label the acids and bases. Okay, so number 2 has this weird format here. This is acetic acid, but it's written like this because like this here. We're gonna do something next year like this. Okay, so it's just trying to emphasize that this proton here, that's where it goes at the end. Okay, so really try not to stress too much about the format. Just look at what happens. This CH3COO negative, oh, there's the anion. Any anion can be a base, but then you look at what it becomes. Okay, so you have CH3COO negative on the right-hand side of the arrow. It's CH3COOH. Did it gain a proton or lose one? It gained. So this is the base because it accepted a proton to become this acid. Okay, now water behaves like HOH, okay? I believe we talked about this when we did double displacement reactions, but this is so important here, okay? So if water is going to be the acid, or it's going to donate the proton, then when you get rid of this H, when it's an acid, then what are you left with? OH. And OH, of course, is a base, and they're a pair. Now you might say to yourself, whoa, Ms. Todd, water is an acid or a base? Yes. Why? Because according to Bronsted-Lowry, an acid is a donor of H's, and a base is an acceptor of H's. It's supposed to be a P, sorry. And that description where you're talking about proton transfer is going to be more important moving forward when you do chemistry. Okay, so try some of the homework questions from the worksheet, the textbook, and like I said, in grade 11, even if this was real, you would only have to do labeling the acids and the bases. You would not have to write your own reactions. Oops. Okay, so any questions, please email me.